So you know what velocity is. Velocity is the same thing as speed. So if you imagine you're driving to Seward and you plot against time how fast you're going. So at minute 1, minute 2, how fast are you going? So if you start off, obviously in your driveway you're going 0, and at some point you're going 95 miles an hour, and then you get behind a really slow car and you're going 35 miles an hour, and then you level off to about the right speed limit, and it sort of goes up and down for a while until you finally end up where you're going. Please don't drive, by the way, 95 miles an hour when you're going to Seward, and if you're in front of me, please don't drive 35 miles an hour when you're going to Seward. But the point is, once you finally get to Seward, you can plot your average speed, and that's the best we can do so far. That's the Algebra 2 level understanding of speed or of velocity. So your average velocity, how long it actually took you to get to Seward. Sometimes you were dragging and weren't going to make it in time, and sometimes you were zooming and we're going to get there early. But the actual time it took you to get to Seward is the slope of the secant line from when you started until when you finished. That's velocity, or that's speed. That's velocity. Obviously you have varying speeds along the way, but average velocity would come from the secant line. The cool thing about calculus is we can actually calculate instantaneous velocity. That's exactly what it sounds like, at an instant. So even though you're speeding up and slowing down and you're constantly changing how fast you're going, I could actually plot, if I had a way to graph this function, if I had a function that described this curve, I'd be able to plot and tell you exactly how fast you were going at that instantaneous, infinitesimally small little spot in time by calculating the slope of the line that's tangent. So the secant line gives you average velocity, and the tan line gives you instantaneous. Oh, I'm not sure how to spell that. Instantaneous velocity. So let's look at an example where both are at play. It's not going to be about speed, or at least not driving speed. It's going to be under the force of gravity. So there's a diver that is on a platform over a swimming pool, and the platform is 32 feet in the air. So the diver's standing here, and the second the diver jumps off, we want to calculate how far is the diver from the surface of the water at any given time. Before that, though, we have to look at some other things that we need to know. First, there's a function that describes this. It's a famous Galileo discovery that things fall at a constantly increasing rate under the force of gravity. So things speed up as they fall. So when you drop a ball from a high surface, it gets faster and faster and faster and faster as it approaches the ground. And the function that describes that is minus 16, and minus is because gravity pulls down toward the earth, t squared, that's at any given time, plus the initial velocity, which makes sense because the initial velocity, if you drop a ball, is going to be at one height after 2 seconds, but if you throw the ball, it'll be at a different height after 2 seconds, plus the initial height, which is obviously makes sense too. How far will the ball be from the ground at any given time? Well, part of it depends on how high it was off the ground when it started. So in this scenario, we have a diver who is going to jump up in the air, and when they start to come back down, just as they cross the threshold of the platform, they've already started to build up speed toward the ground. So we have the f of x, or in this case the s of t, equals, and I actually like to use the h of t, for the height at any given time, is negative 16 t squared. The initial velocity from where we start to measure is 16 t, and then the initial height, of course, is 32. 2. And so the scenario that we've set up is, at any given point along this path, what is the height that this diver is going to be after a certain number of seconds or whatever. So the first question that we want to answer, or we're asked to answer and will answer and need to answer to be able to get to the second question, is exactly how long does it take for the diver to hit the water and splash down? So how long till the diver, not tilling a field, till the diver hits the surface? Of the water. Okay, so that is just a how long did it take problem. Here's a function of time. How long did it take? We can totally solve this one just using Algebra 2. What we care about is, because this function says how high off the ground the diver is at a given time, we know that when the diver hits the water, the surface of the water, their height off of the ground is 0 because they've come back to the ground. That's exactly what the formula tells us. So we want to solve this problem for 0. We want to find out what t is so we know how long it took. So I'm going to factor out -16 first. Now I can factor. And I get two choices. T equals 2, so after 2 seconds, or t equals -1, so in -1 seconds. So -1 is a perfectly respectable answer for this function. It just doesn't happen to describe the real world scenario, because nobody hits the surface of the water 1 second before they jump. No matter how good they are, they're unable to do that. So t equals 2 is the answer, so after 2 seconds. Now here's where the calculus comes. The second part of the question is exactly how fast, what is the velocity that the diver is falling at the second they hit the water? So what is the velocity? And that would be the instantaneous, and we all know I don't know how to spell that. I'm not even going to try. What is the instantaneous velocity when the diver hits the water? And this one is calculus. And you know it's calculus because it says instantaneous, and that's what calculus is always all about. So let's calculate that. So if h of t is the average velocity, how long did the whole trip down take? If the h of t has to do with average velocity, we can say that the derivative, the h prime of t, is the instantaneous velocity at some time t. So let's calculate the derivative of this function. I'm going to come back up here to the beginning. So the derivative of -16t squared is 2 times -16, -32t, to the 2 minus 1, so just to the first power, plus 16, constant multiple rule, times the derivative of t, but the derivative of t is just 1, and then plus the derivative of 32. 32 is a constant, so the derivative of 32 is 0. So this is actually our function that describes instantaneous velocity at any given time. So if I want to know exactly how fast this diver is going 1 second after they crossed this plane, I can put a 1 in for t and it'll tell me exactly how fast they were going at that very instant. If I want to know at 1.5 seconds, I can just put in 1.5 and it'll tell me the instantaneous velocity. But I want to know about 2 seconds because that's the instant the diver hits the water. So the h prime of 2 equals negative 32 times 2 plus 16, which equals, yikes, negative 64 plus 16. Oh, I didn't know I was going to have to do hard math today. Negative 64 plus 16, negative 54, negative 48. So negative 48 feet per second. I forgot my units for a minute. Feet per second. And the negative just means that the diver is moving toward the earth. Positive means moving away from the earth, and negative means moving toward the earth. So I can say that the instantaneous velocity when the diver hits the water is negative 48 feet per second, or 48 feet per second. Depending on how you word it or phrase it, you could make that negative or positive. So a function calculated in Algebra 2 describes averages. So if I had a function for how much energy my body used during a day, if I had a function for it, I'd have to have a function for it. If I did, then that function could be used to tell me the average amount of energy I used over the course of the day. At any given moment, the average amount would come from Calc 2. So the function gives me the average amount. The derivative of that same function then would have the ability to give me the instantaneous amount. What is the amount I'm consuming when I'm rushing into work? What's the amount I'm consuming when I'm settling down to dinner? What's the amount I'm consuming at different times of the day doing different things? Instantaneous. Okay, I've got to learn. Interestingly enough, I can spell it when I'm typing. And let's move on. A little preview, there's something called the second derivative, which is when you take the derivative of the derivative, and that tells you the instantaneous change in velocity, the acceleration. That's pretty cool, huh? And then the third derivative gives you jerk, right? So sometimes something doesn't just start to accelerate faster, it just goes from it goes from one speed to another instantaneously without having to progress through putting your foot on the pedal and moving forward. Okay, little advertising of all the cool things you can do with calculus. What we need to know for now is that instantaneous velocity is our new friend, our new tool available to us through calculus.